The mechanism shown is used to lower disabled persons into a whirlpool tub for therapeutic treatment. In the unloaded configuration, the weight of the boom and the hanging chair induces a compressive force of 575 newtons in hydraulic cylinder AB. Compressive means that the force which cylinder AB exerts on point B is directed from A toward B. Let's go ahead and draw that force the way that it would act. So we'll get our force arrow, and that force we could think of as acting on point B. So the cylinder is being compressed, and so it would feel a downward type load from the weight of the structure above it, but it would push back up on point B and sort of hold point B up, as it were. We're told that the angle theta is 30 degrees. We can see theta here. So theta gives us the orientation of this bar. And in addition to that, it's going to be used when we look at the distance that point B is down on this little support leg here on the lower boom portion. Okay, so that will also have theta come into play. We'll deal with that in a minute. We want to determine the moment of this force, the way it's oriented on the picture, as it acts on point, or as it acts here at B, around point O, and then also around point C. So we're really just looking to find a moment here. Now, let's go ahead and label this force, and we'll label this as F AB. So it's the force in cylinder AB, and we need to find an angle. We know the magnitude of this force, but if we're going to take a moment, we're going to have its components, and in order to get the components, we're going to have some sort of an angle which orients us with respect to the frame here. So let's put in a horizontal line down here at A, and then we can simply say that this angle is phi, and I'll use phi to write the components. Alright, so I've got to figure out what this angle phi is, and it's not terribly difficult, but we do need to be careful. So let me move that label really quick. Let's look at the right triangle that is formed, and let's use a different color so we don't get things sort of confused here. But let's look at the right triangle that is formed in going from A to B with the cylinder sort of as the hypotenuse. Alright, so we have the angle phi, and it would be easy to see that phi could be written, if we call this H and we call this B, then phi is the tan inverse of H over B. Now, how do we get H? Well, H could be seen is the vertical height from A to B. So in going from A to B, if we kind of go out here and go up the support mast, we're going to first go up by 800. So let's write this out. So we're going to first go up by 800. Then we're going to go up by 175 and 100, and that gets us vertically up to this pin. So plus 175 plus 100. Now, we then need to determine the vertical rise that we would have in getting from this pin to this point right here, where we can begin to head perpendicular to this lower boom down to point B. So let me draw another little triangle in here. Okay. The height of this leg of the triangle can be seen as 400 times the sine of theta. So we can write that. And then I have to go down from this point right here down to point B. So let me sketch one last triangle. Try to use maybe a green one, or let's just go with a pink triangle here. Yeah, I can't really make it small enough. Oh well. Let's just delete that. we've got to get from here down to B. And this height, if we zoom in here for a minute, if I've tilted this boom up by theta, then that means I have the same angle right there. So this angle in here is also theta. And so this vertical height is 150 times the cosine of theta. But I'm going downward with it, and so I will subtract it from the previous value. So minus 150 cosine of theta. And that is the numerator in this expression. So let's now work on the denominator. And this is really the longest part of this problem. So once we have this, it'll be easy. For the distance b, all right, in going from A to B, if I think about the left edge here as sort of my starting point, kind of where point O is, then B plus 200, the total horizontal distance from here to here, would be the same as the horizontal travel from a vertical line through C out to point B. And so the easiest way to do this is to just start over here at the left edge. We're going to go out 175. Then we're going to go the horizontal side of our orange triangle, which is 400 times the cosine of theta. Then we have to go out the horizontal side of our pink triangle, which is 150 times the sine of theta. And then we have to remember that point B is 200 millimeters to the right of that vertical line we started on. So we subtract 200. And that will allow us to compute the angle phi. And if you do the calculation, you will find that phi is 70.9 degrees. And that really is the hardest part of this problem. So once we have phi, we're ready to work or to do our moments. So let's clean the picture up slightly. Get rid of B, and I'm going to get rid of my little triangles up here. I'm not going to need those. Okay, so we have our force, FAB, and for simplicity, I'm going to move our force. Forces operate according to the principle of transmissibility, and I'm going to let this force act as if it was pulling on point A. That's the same line of action in space, and there's nothing wrong with letting the force act right there. So if I do that, I can sketch the components really quick, and I won't label them, but I will sketch them. So I have a horizontal component, and then I have a vertical component, and it's going to be very easy to take moments with this horizontal and vertical component around the pins that I want. So let's pick a direction as positive. We will take counterclockwise moments as positive. And let's do the moment around point O, the moment around point C. So for the moment around point O, we have the vertical component, which is FAB times the sine of phi. And that has a moment arm of 200 millimeters away from O, and it will produce a counterclockwise moment. So times 200 divided by 1,000. Then I have the horizontal component, FAB, times the cosine of phi, and that will produce a clockwise moment around point O, and it also has a moment arm of 200 millimeters. So minus 200 divided by 1,000. So we can substitute. So this equals 200 divided by 1,000 times FAB was 575. So 575 times the sine of 70.9 degrees, and then minus the same force, 575, this time with the cosine of 70.9 degrees. And if we do the math, we will find that MO is a positive 71.1 Newton meters, and the positive tells us that it's counterclockwise. So there's the moment around point O. And now we can do the moment around point C. We'll keep the same convention. The vertical component of the force is also going to produce a counterclockwise moment around C, and it has the same moment arm. So we have another 200 divided by 1,000 times FAB, sine of the angle. This time the horizontal component of the force will produce a counterclockwise moment around point C. This time it has an 800 millimeter moment arm. So plus 800 divided by 1,000 FAB cosine of the angle. So we can substitute 200 by 1,000 times 575 cosine 70.9 degrees, and then plus 800 divided by 1,000 times 575 sine 70.9 degrees. And if we add these two quantities together, we'll find that the moment around point C is equal to 259, it's positive, Newton meters counterclockwise. And that's all we have to do for this problem. So it really is true that the hardest part of the problem is getting the angle of orientation for the force in the cylinder. But once we got that, being very careful as we went up and over from A to B, sort of around the structure on the dimensions that we knew, that once we got that angle in place, it was very easy to use transmissibility to move the force from B to A, because it's very easy to see where the components of the force act when they're at point A. It's a little harder to see when they're at point B. We could have done it that way, but it's much better practice to move them to the point that's easiest to work with. All right, so that is our lifting mechanism.